This video lecture accompanies Learning IoT with Python and Raspberry Pi. In this video lecture, we will write several functions to sort and search lists. Go to the main menu, select Programming, and then select the Thani Python IDE. The first two functions we create will be utility functions. The first function we will write will print the elements that are in the list. We'll pass in a single parameter called a list to this function. We'll create a for loop by writing for I in range up to the length of a list. And we'll print out each element in the list with 5 spaces, and we don't want to go to a new line, so we'll set the end just equal to a space. We'll call the printf function outside of the loop to go to a new line. Let's write a main function where we'll define our initial list, iList, and set the values of the elements. We'll call the printlist function and pass in iList as an argument. And let's call the main function. I'll name this file sort search. And let's run this code. Let's next write a mySwap function, which is going to be used to swap the values of 2 elements inside of a list. This will allow us to do an in-place sort. So I'll pass in 3 parameters, a list and I and j, and I and j are the indices of the elements which I want to swap. I'll save the element that's at index I into a temp variable. I'll overwrite the element at index I with the value of the element at index j. Then I'll assign the value of temp to the element that's at index j. The first algorithm for sorting, which we'll implement, is the bubble sort. This compares the values of the current element in the list with the remaining elements in the list. If the value of the current element is greater than one of the remaining elements, the values of the elements are swapped. My current element is shown in green. The remaining elements in the list are shown in blue. 3 is greater than 1, thus we swap the element. Now that element, the element at index 0, is the least element. Then 3 again is compared with the remaining elements in the list. There happens to be another 1 in the list, so those 2 elements are swapped. My next current element has a value of 4. 4 is greater than 3, thus we swap. 5 is greater than 4, and thus those elements are swapped. And this continues until the entire list is sorted in ascending order. Let's next go back to our Thani Python IDE and write a function which implements the bubble sort algorithm. So for our I in range up to the end of the list, that I is going to be our current element, and we want to compare that value with all of the remaining elements in the list. So we'll do for j in range I plus 1 to the last element in the list. If our current element is greater than the elements that are in the unsorted part of our list, then we're going to swap. Now I'm also going to call the print list function, passing in a list, so that we can see how the elements are sorted after swapping two elements. I'll call the bubble sort function, passing an iList, and I'll print the list out after it's been sorted as well by calling the print list function once again. And you can see that these elements have been sorted in ascending order. Let's next look at the insertion sort algorithm. The insertion sort algorithm compares the values of the pairs of elements. If the value of the previous element is greater than the value of the current element, the values of the elements are swapped. My current element is shown in green. The previous element is shown in purple. 3 is greater than 1, so those elements are swapped. 4 is greater than 1, thus those elements are swapped. 9 is greater than 6, thus those elements are swapped. And this continues until all of the elements are sorted in ascending order. Let's next write the code that implements the insertion sort. We'll again pass in a single parameter, a list, and for our outer loop, we'll do from I in range to the length of our list. And because we wish to compare pairs of elements, we'll set our index j equal to our index I. And while our j is greater than 0, and while the value of the previous element is greater than the value of the current element, I'll swap the value of the previous element with the value of the current element. And I'll print out the elements in the list at each iteration. And I'll decrement the index j, since I'm comparing pairs of elements, all the way back to the second element in my list. That's the element at index j is equal to 1. Because remember, with my loop, I'm continuing while j is greater than 0. And then let's run this code. And again, we can see that the elements were sorted in ascending order. Let's next look at the selection sort. The selection sort algorithm finds the element with the largest value in the unsorted part of the list and swaps it with the last element in the unsorted part of the list. The last element in the unsorted part of the list now becomes part of the sorted subset. The sorted subset has the elements which are sorted in ascending order. So initially, we have the unsorted list of elements. The largest element in this unsorted subset is a number 9. That's swapped with the last element in the list. That 9 is now part of the sorted subset. The unsorted part of the list is next examined and the largest element is found. This value is swapped with the last element in the unsorted part of the list. Now, our sorted subset has 6 and 9. This continues until all of the elements, except for the element at index 0, are part of the sorted subset. Let's create a function that's called selection sort. That function will take a single parameter, a list. Initially, our entire list is unsorted. So we'll do for I in range, the length of the list down to 0 is not inclusive of 1 and increments of -1. Index max is going to be the index of the maximum element in the unsorted part of the list. We're going to look at all of the elements in the unsorted part of the list, so we'll do for I in range 1, 2, I, and we'll search for the element that has the largest value. If we find an element that has a value that's greater than the element at index max, we're going to determine that there's a new value for index max. Once we found the index of the element that has the largest value in the unsorted part of the list, we're going to swap the value of that element with the last element in the unsorted part of the list. The last element is now part of the sorted subset. At the next iteration, we search just that unsorted part of the list, again going to the last element -1, finding the index of the maximum element, and then swapping that value with the last element in the unsorted part of the list. This continues until all of the elements except the element at index 0 are part of the sorted subset. The element at index 0 will have the smallest value, since we determined the largest value in the unsorted part of the list at each iteration, and swap that value with the last element in the unsorted part of the list. Let's next look at searching. We'll first look at the sequential search. The sequential search algorithm compares the search key with each element in the list until a match is found, or a match is not found after the value of each element in the array has been compared with the search key. The sequential search function will return the value of the index of the element that contains the search key, or a -1 if the search key was not found in the list. The sequential search function takes two parameters: a search key and a list. The result variable will hold the index of the element which has a value which matches the search key. Initially, we'll set result equal to -1 in case we don't actually find a match. So we'll search through each element in the list to see if the value is equal to the search key. If it is, we'll set result equal to I, and we'll break out of that loop. If we find a match, result will have the index of the element that matches the search key. If we search through the entire list without finding a match, result will be equal to -1. The function returns the value of result. We'll prompt the user to enter the value which they want to find in the list. We'll call the sequential search function and pass in two arguments, find and iList, and we'll store the return value in index. If our index is not equal to -1, we'll print out match found at index and the value of index. Otherwise, we'll print out match not found. Let's run this code. Now you notice that a match was actually found at index 6. Now I could run the sequential search without first having to sort the elements in my list. Let's run this code a second time. And you'll notice this time I typed in a value which did not exist in the list, and thus I see printed match not found. Let's next look at the binary search algorithm. The binary search algorithm requires that a list be sorted. It successively divides the array in half based upon whether the search key value is greater than or less than the middle element. A new high or low limit is set for the range of elements to be searched. This continues until a match is found or the low index is greater than the high index, and in that case, a match is not found. Let's next create the binary search function. We'll pass in the search key as one of our parameters and a list as the second parameter. The value of low will be equal to 0. Initially, we're going to be searching the entire list, and our value of high will be the length of the list minus 1. While our low is less than or equal to high, and these are the indices over which we're searching, we're going to compute the middle. The middle is going to be the sum of the low and high index divided by 2. And I'll print out the values of low, high, and middle. If the value of our element at index middle is equal to our search key, we'll set result equal to middle, because now we found a match, and we'll break out of this loop. If the value of the element at index middle is less than the search key, then our low is going to be equal to middle plus 1. That means that we're going to search the upper part of the list. Otherwise, the upper part of our list, our high, is going to be equal to middle minus 1. In this case, the value of the A list middle is greater than the search key. That means that we'll only need to search in the lower half of the list. The list is successively divided in half until we find a match, or until our low is greater than high. If our low is greater than high, our result is set equal to -1 because a match wasn't found. In any case, we'll return result from the binary search function. Before calling the binary search function, we'll need to sort the list into ascending order. So we'll call the selection sort before calling the binary search function. We'll pass in 2 arguments, find and iList. Let me print out the order in which the elements are stored in the I list after calling the selection sort, and let's run this code. Initially, our low was equal to 0, our high was equal to 8, and our middle was equal to 4. Our A list middle is less than our search key. That means we need to search the upper part of the list. Our low is equal to middle plus 1, that's 4 plus 1. Our low is equal to 5, our high is equal to 8. Our middle is going to be equal to 6. A list middle is going to be less than the search key once again. Our low is going to be middle plus 1, that's 6 plus 1. Our low is equal to 7. Our high is equal to 8. Our middle is equal to 7. Our A list middle is equal to the search key. Thus, a match was found.
This video accompanies Learning IoT with Python and Raspberry Pi. For more information, go to www.learningiot.net.